In the name of Allah, the most beneficent and the most merciful. Today we would like to start our fifth chapter, which is the last chapter from my side. And the name of the chapter is Unsteady Flow. And I am taking this chapter from the book of Fluid Mechanics with Engineering Applications by R.L Daugherty, Frenzini, and Finnemore. And in that book, it is the 13th chapter of the book. So I would recommend that you should also consult books. And now there will be one quiz which will be from the books. I mean, for example, what is the name of the book, complete title of the book, its year of publication, etc. As you should be able to refer the books. Okay. And let us start the definition, very basic definition of the unsteady flow that I think we already know very well. So it is a type of flow in which flow parameters are conditions of flow that remain constant with respect to time at a particular section of the conduit. And that flow is unsteady flow. So mathematically, how we can define this unsteady flow by these expressions? What is the number one? Dy over dt is not equal to 0. It means the depth of flow does not remain constant with respect to time, and it is changing. So this first expression is valid for which conduit? For the pipeline or for open channels?
For open channels.
Yes, for open channels. You know, if the depth of flow in an open channel is keep on changing with time at a particular section, then we say that this is the unsteady flow. What is the next expression? dV over dt is not equal to 0. It means the velocity of flow at a particular section is keep on changing, is not constant. So this expression, what do you think? Is it applicable for open channel flow or for pipe flow? Yes, please.
For both, sir.
Yes, for both. Very good. This expression is applicable for both, maybe a pipe, pressure conduit, or an open channel. In both cases, if the velocity of flow is changing with respect to time at a particular section, then this would be unsteady flow. Now the next expression is dq over dt is not equal to 0. It means the discharge or the flow rate is changing with respect to time at a particular section of the channel of the conduit. So this expression, what do you think? Is it applicable for pipe flow or for open channel flow?
For both, sir.
Yes, for both. This is all right. Now the next expression is change in pressure with respect to time is not equal to 0. So it means at a particular section of the conduit, the pressure is changing with respect to time. And this expression, what do you think? Is applicable for open channel flow or for pipe flow?
For pipe flow, sir.
Yes, it should be for pipe flow because fluid flows under pressure. Only in pressure conduits or pipes. In open channels, it has a free surface. And how much is pressure on the free surface?
Atmospheric pressure.
Atmospheric pressure. Or how much its value would be in terms of gauge pressure?
0.
Yes, it would be 0. So this is all about the unsteady flow. Now, what are the various famous or very important examples of unsteady flow which we would like to take up as a study in this chapter? So those examples of the unsteady flow are 3, which we will inshallah cover in this chapter. What is the number 1? Discharge through orifices and over wears under varying head. Under varying heads. If the head is changing, then which type of flow it would be from the orifice? I think you know very well what are orifices. Orifices are the basically openings at the bottom or side of tanks to discharge the liquids. Those are orifices. And suppose if we have a tank and if there is an orifice in the bottom or on the side, and if there is no inflow in the tank and only there is outflow from the tank, then what will happen to the water level with time? Would it remain same?
Decrease.
That will decrease. So it means small h, which is the head causing the flow, would it remain same? Would it change or it will remain same? H, head causing the flow. Please respond me.
Decrease, sir.
It will change, sir.
It will decrease. So it will decrease. And you know, the velocity of flow from the orifice and the discharge through orifice is not a function of small h. But what is your opinion? Yes, it is function of small h. So as the h decreases, so velocity of flow from the orifice decreases. As the h decreases, the flow rate from the orifice decreases. So what happens then? Does this flow remains steady?
No, sir. Unsteady.
Yes, that flow is unsteady because the head is continuously decreasing. And you know, sometimes there may be some inflow. And when the inflow is more than the outflow, then the storage in the reservoir keep on increasing. And that's why due to that head will increase. And then the flow rate will increase. So even in that case, the flow would be unsteady if the head is keep on changing. All right. And you know, then if we have a constant discharge, then we can easily compute the emptying time of a tank. What is equal to discharge? Discharge is equal to volume over time. And we know the volume of the tank. So we can compute the time required to empty the tank. But if the flow is unsteady, as the case of in real tanks, what are the example of tanks? Like overhead tanks of a housing society. Okay. Have you seen housing societies? No, have you seen overhead tanks in those housing
Yes.
societies? Yes. So as the water level comes down, the head reduces and that causes the unsteady flow. And also it makes difficult to compute the emptying time because now the discharge is not constant. So anyway, this is the first example of the unsteady flow, that is the discharge through orifices of tanks and over weirs under changing heads. Now come to the next example. Unsteady flow through pipelines due to opening and closing of valves. We know very well, whenever we provide a valve and we at the end of a pipeline and we open the valve, once the valve is completely closed in the pipeline, how much is the velocity of flow?
0, sir.
0. As you open and the pressure is, static pressure is highest, and as you open the valve, so velocity of flow will keep on increasing, and as we open more and more, the velocity of flow will further increase, but the pressure in the pipe will reduce. Similarly, when we close the valve, what is happening? So the pressure inside the pipe will be keep on increasing, whereas the velocity of flow will keep on decreasing due to closing of. So it means this closing and opening of the valve of a pipeline is a very good example of unsteady flow in the pipelines. And what is the practical example? I am not talking only of the water taps which we have in the houses. Its more practical example is in case of the hydropower plants. Do you know in case of hydropower plants, water comes through penstocks under very high pressure, and then it is supplied to the turbine runners. So if we have an impulse turbine, can you tell me what is the valve practically in impulse turbines? What is the name of the valve?
Governor?
No, not governor.
Spear-headed needle.
Oh yes,
spear-headed needle.
This spear-headed needle, which moves in axial forward direction and closes the opening of the nozzle. And what is the example of the valve in case of reaction turbines?
Movable guide blades.
Very good. Those are movable guide blades. Can you see these? They move like that. So now this is the passage of flow. So once they come, they move in this direction. So the openings, those are closed and they act as a valve. Do you know that if these valves are suddenly closed, what will happen in the pipeline? There will be very high pressure, dynamic pressure in the pipelines. If the pipeline is not properly designed, then these pipelines may burst due to that very high pressure. And that very high pressure is known as, it will create water hammer in the pipelines. Okay, so water hammer basically is an example of the unsteady flow. What is the third example of the unsteady flow? Suppose if we have an open channel and if we have a hydraulic structure and we close the gates of a hydraulic structure immediately, then what will happen on the upstream side? A surge wave will generate and the depth of flow will change. That is also an example of unsteady flow, but this is in open channels. Okay, so these three are very famous examples of unsteady flow, which may cause problems in the engineering structures, and that's why we will study, inshallah, all these three. Any question till now? If you have any question, you are welcome.
सर ये वाटर हैमर के बारे में दोबारा काइंडली बता दें.
Water hammer, of course, we will discuss in detail in this chapter. But very quickly, I would mention that suppose if we have a pipeline and we close the valve suddenly, then a pressure wave moves in the direction opposite to the valve, and then it comes back and again goes back and come back. So that causes the positive and negative pressures for a short length of the pipe, and that is called as water hammer. Okay, so it produces a very high dynamic pressure. और उसकी waves चलती हैं, positive wave and forward wave, forward wave, backward wave, unless it is damped. So that is called as water hammer. We will discuss in detail, maybe in next lecture, inshallah. But for this, for today, I think it is enough. Any other?
No, sir.
Okay, now we want to basically derive expression for the unsteady flow through orifices. Now we are considering this reservoir. This is a reservoir and it has certain inflow Q1 and certain outflow Q2, and here there is an orifice. And small h is the head over the orifice, which causes the flow. So this small h is a variable. Do you think is it a variable? Or it is
Yes.
a constant? Yes.
It's a constant.
No, it is not constant. For example, yes, when it would be constant, when the Q1 would be exactly equal to Q2, then the H will not change and the H will become constant. And at that time, the flow through the orifice won't be unsteady. The flow would be, कौन सा होगा?
Steady.
Steady flow. Yes. Now, let's say the DH is the drop in the water level in the reservoir in time dt. Dt is a very small interval of time. Okay. And capital A is the surface area of the reservoir. Now, what are the practical examples of the reservoirs? Can you give me some few examples? Yeah, one of the example is overhead tanks, as I mentioned you, है ना? So we give inflow to the tank, and also we take outflow from the tank. So overhead tanks are basically one of the example of unsteady flow. Reservoirs. What is the another example of reservoirs other than the overhead tanks? What about Tarbela Reservoir? What about Mangla Reservoir? They have also the similar conceptual diagrams. They have also inflows. They have also outflows. They have also surface area. Is it true? Kyun bhai?
Yes, sir.
So Tarbela and Mangla Reservoir, they are also like this. We can represent them in this way. So, okay, now we want to derive the expression for the time to empty the reservoir. So consider a reservoir of irregular shape. Now, what is this shape? Is this shape regular or irregular? It is irregular shape. This is not a rectangular, neither triangular, neither trapezoidal. So it is a regular shape with certain inflow and outflow. That is Q1 and Q2 respectively. And these I have already explained that dH is the change in head in time dt, and capital A is the surface area of the reservoir. Then what would be A times dH? So this is the volume, so which has been lost by the reservoir in time dt. Or in simple words, we can say that change in volume of reservoir in time dt. Now for unsteady flow, it is necessary that Q1 should not be equal to Q2. If they are equal, then the flow would be steady. and the change in volume in time dt would be area times dH. That is the incoming volume minus outgoing volume. And how we can compute the incoming volume in time dt? That is Q1 into dt. This is the volume of water which enters in the reservoir. Minus Q2 dt. This is the volume of water which leaves the reservoir, or outflow from the reservoir in time dt. And you know this is equal to area times dH. So rearranging this equation, we can say that the dt, that is equal to area times dH, Q1 minus Q2. And you know there is here derivative, and how we can get rid of this derivative? By integrating equation number 1. So by integrating this for time limits from 0 to t, and the limits of the reservoir levels from H1 to H2. So what is the finally result? That is the equation number 2, in which the small t, that is equal to H1 to H2, area times dH, Q1 minus Q2. And this is the expression for emptying time of the reservoir from levels or heads from one head to another head. Is it clear? Yes, I want to know your response. But you know, for a steady flow, Q1 is equal to Q2 because the H remains constant. And for the actual discharge, we can easily compute CDA root of 2GH because H is constant. But here, computing time is very easy if the flow is steady. But you know, we are discussing unsteady flow, and for unsteady flow, so emptying time, small t, we can compute by using this equation. If Q1 is equal to 0, suppose there is no inflow, then of course we will put Q1 0, and the same equation number 2 will become like this. T is equal to integral with limits H1, H2, area times dH over Q2, and this is with negative sign. And equation 2 and 3 can be solved or evaluated only when values of A and Q are written as a function of H. What do you think? We have to do integration. And that's why if it's possible that we can write surface area in terms of H, or we can write discharge Q2 or Q1 in terms of H, then we can do integration. Do you agree? Yes, I want to hear from your side. Do you?
Yes, sir.
Yes, sir.
Because we have to integrate. And how we will integrate? Either we should write, we must write Q2 in terms of H. And if possible, we should also write surface area of the reservoir in terms of H, if possible. Okay? And you know, if there is an orifice in the bottom of the reservoir or vessel, then this equation we can easily derive from this equation, that the emptying time emptying time would be 2a CdA root of 2g and under root h1 minus h2, where h2 is the initial head and h1 is the final head, or vice versa, it depends on you. And then you can compute the time required to lower down the level of the reservoir when there is unsteady flow through the orifice. So now the question is, in case of vessels of regular geometry, if, for example, if overhead tank we have of cylindrical shape, if we have of conical shape, and then and A and Q we can easily write as a function of this small h. But you know, however, for vessels of irregular shape, this is not possible. Then how we can find the emptying time? But you follow my point? So we can easily solve this equation by writing Q2 in terms of h, or sometimes surface area also in terms of h. But if it is a reservoir of irregular shape, like Tarbela reservoir, like Mangla reservoir, then what we have to do? We can find emptying time by graphical method. Okay. And what is that graphical method? We have to compute numerical values of A over Q1 minus Q2 for corresponding values of small h. So we have to make a table. We will write here h values, small h values, and the value of this parameter capital A over Q1 minus Q2. And then we will plot a graph between the h and area over Q1 minus Q2. Suppose this is the graph, then as per equation number 2, if I plot a graph between the small h and area over Q1 minus Q2, what it should be? Yes, it is my question to you. जी भाई, are you hearing? क्या होना चाहिए? अगर if I am plotting on y-axis small h, which is the head, on an x-axis this parameter a over q1 minus q2, तो इन दोनों की प्रोडक्ट क्या है?
सर टाइम आएगा, एरिया अंडर द कर्व.
Area under the curve would be the emptying time of the reservoir. ठीक हो गया? So the emptying time, how we can compute in case of irregular shape reservoirs, we have to plot the value of h on y-axis and this parameter capital A over Q1 minus Q2 on x-axis, and the area under curve we will determine. That would be the emptying time, because if we multiply this with this, what would be the units of the outcome? क्या यूनिट निकलेंगे? टाइम के यूनिट. Okay. So with that, now we are going towards the numerical, and we want to apply that equation number 2 or equation number 3, which we have derived. Now problem number 1, a cylindrical vessel with its axis vertical is filled. What do you mean by with x vertical? It means it's a cylindrical vessel and its axis is vertical, is filled with water and discharges through a 2 centimeter diameter orifice at bottom. So this is an orifice at the bottom and its diameter is 2 centimeter. CD is 0.62. The coefficient of discharge of this orifice is 0.62. And it is a cylindrical vessel. So this is the plan of the tank. Okay. And this is the elevation side view. If the dia of vessel is 60 centimeter, if this diameter is 60 centimeter, find the time required for the water level to drop from 2 meter to 1 meter above the orifice. If the initially water level is here, 2 meter, and if we want to drop it to 1 meter over the orifice, so it means H2 is 2 meter and H1 is 1 meter, then how much time would be required to drop the water level from 2 meter to 1 meter over the orifice? That is the question. So it means we have to compute small t. Okay. So this is the data given, and how we can solve it. I want to know only the concept. We have to apply that equation, that small t, that is equal to integral with limits h1 to h2. Then area times dh divided by q1 minus q2. Okay, here q1 is how much?
0, sir.
0. There is no inflow, so there is only outflow from here. So we have to apply that equation. And here, what about this surface area? Does it changes with change in head? This is the small h. Does it changes with change in head?
No, sir.
No. It means in which the small h variable can appear, that is only the equation for Q2. Anna? What would be the Q2? Area into velocity. All right. So that we have to solve. So the solution is here. Now this is the over equation, h1 to h2 minus adh over q. First of all, compute the area of this cylinder. This is the diagram. This is the 2 meter, this is 1 meter, and this 2 centimeter orifice. And how we can compute the area of this cylinder or tank, pi by 4d square, and capital D is 60, so divided by 100 square, that is equal to 0.2823 square meters is the surface area of the this cylinder. Now compute small a, which is the area, cross-sectional area of orifice, pi by 4d square, and the answer you will get 0.314 into 10 raised to power minus 3 square meters. Now we have to compute the discharge through this orifice in terms of h, that is the CD into A into root of 2gh. And if we will put these values, and in terms of h, we will get the value of the q like this, 0.863 into 10 raised to power minus 3 root of h. Now, using the equation for emptying time, small t, that is the integral h1 to h2 minus 0. This is the area, surface area, over this one is the discharge in terms of h into dh. So what we have to do, we have to integrate it. So this root of h, when it will go as numerator, its power would be minus half. And this is a very simple integration. That would be x raised to n plus 1 over n plus 1. So what would be its derivative? Its integral. Its integration is very easy. And that would be 2 times this h raised to half, and then apply limits, these limits, and when you will put these limits and after solving, you will get the emptying time is 271.2 seconds or 4.52 minutes. So this is the solution of the problem. So the time taken to lower this water level from 2 meter to 1 meter in the reservoir would be 4.5 minutes. Any question in this problem?
No, sir.
Okay. You know, the same problem you can also solve directly with this equation, which we can derive in the same way as we are solving this numerical. यही equation है ना? क्यों भाई? ये equation. ये वही equation है ना? This is the same equation. Now we want to solve another problem. Problem number 2. A cylindrical tank. Again, the tank is cylindrical. It is circular in plan. 3 feet dia. Its diameter is 3 feet. So this dia is 3 feet. Is emptied through a 2-inch dia pipe. So there is a pipeline. And its diameter is how much? 2 inches. Which has both ends sharp. This end is also sharp. And this end is also sharp. And has small f 0.04. What is this small f?
Friction factor.
Yes, friction factor. Find the time taken for the head over the orifice to fall through 8 feet to 4 feet. If the head initially is 8 feet above this pipeline, and if this head has to reduce to 4 feet, I mean we have to empty this much tank, then what time would be required? There is no inflow, so Q1 is 0. Length of the pipe is 12 feet. So from here to here, this is the length of pipe and it is 12 feet, which we have mentioned here. So how we can solve this problem? You know, in the same way, the basic equation will remain same. The emptying time is integral H1, H2 limits, and then area times DH divided by Q1 minus Q2. But the only thing is we have to write Q2 in terms of H. And that how we can write that? By applying, you know, energy equation between this point and that point. Am I right? Then what would be the energy equation between this section number 1 and section number 2? That would be the, taking this as a datum, that would be Z1 plus P1 over gamma plus V1 square over 2G. That should be equal to Z2 plus P2 over gamma plus V2 square over 2G plus what? What else? What else we require?
Head loss?
Yes,
Friction
head
factor जो है.
loss. Yes, very good, head loss. Now, what do you think, which type of the losses will occur when the fluid will flow, water will flow in this pipe? The first loss would be entrance loss. And if this is flush, then how much would be the entrance loss? 0.5 V square over 2G. Hai? Then the next loss would be loss of head due to friction. And how we can compute that loss? Major loss कैसे निकालते हैं?
Darcy-Weisbach equation.
Very good. By using Darcy-Weisbach equation, FLV square over 2GD. All right, now the solution of this problem is here. Now, first of all, you have to make this diagram. So this is the pipeline, its dia is 2 inches. Let's say this is the small h, because we have to write the equation for Q2 in terms of h, because we have to integrate it. And this length of pipe is 12 feet and so on. So compute capital A, pi by 4d square, and this is 7.07 square feet. Then the small a, which is the area of this pipe, pi by 4d square, and that is 0.0218 square feet. Now, as I mentioned, you applying energy equation between section 1 and 2. Section 1 is here, section 2 is here. And this is the energy equation. Z1 plus P1 over gamma plus V1 square over 2G. That is equal to Z2 plus P2 over gamma plus V2 square over 2G plus head loss. So Z1 is H and P1, how much is pressure here? That is 0. How much is the velocity here? That is 0. Z2, as we are taking this as datum, so 0. How much is the pressure here? A liquid trajectory has 0 pressure because it is open to atmosphere. How much is the velocity? Yes, velocity would be V2 square over 2G, and head loss would be entrance loss plus friction loss. Now, if you will further solve this, it will become like this and this. And what you can do, you can compute the velocity of flow in terms of h. So velocity is equal to 3.83 root of h. And if I know the velocity of flow in this pipeline, what would be the discharge? Area into velocity. This is basically Q2, huh? And if you will multiply this with area, you will get 0.0835 root of h. So what we did, we wrote the value of the Q in terms of h. Now it is very easy putting the values in this equation. So small d is integral with limits h1 to h2 area dh over q. Put values and solve it, and then you will get the answer 140.5 seconds or 130 seconds. So please check what is the correct answer. So this is how you can solve this problem. So this much time is required to drop this water level in the tank from this to that. Even you can compute the time to completely empty the this tank, and then the value of this would be, instead of 4, it should be 0. Okay? Any question? Yes, please.
सर
Are you
काइंडली
connect?
मेंशन कर सकते हैं कि सेक्शन 1 और सेक्शन 2 कहाँ पर है?
Yes,
जहाँ पे
yes.
सर जहाँ पे एनर्जी इक्वेशन लगाइए सर।
मैं बिल्कुल बता देते हैं। देखो, सेक्शन 1 है यहाँ, ये लिखा नहीं गया है यहाँ पे, यहाँ लिख लें आप। दिस इज सेक्शन 1 which is the free surface, and this is the section 2. सेक्शन 2 से क्या हो रहा है? लिक्विड बाहर आ रही है, यहाँ लिक्विड भी बनाए आप, ठीक है? यहाँ से लिक्विड बाहर आ रही है. So this is the section 2. Now if you have any question, you are welcome.
सर ये सेक्शन 1 पे वेलोसिटी क्यों 0 हो गई है?
Section 1 पे velocity 0 इसलिए because the water is it has a free surface. So
ड्रॉप तो हो रहा है ना?
yes, very good. You are right. The liquid is dropping, but if its diameter is too large, that drop is so small that we can ignore. ठीक है ना? Any other question? So shall we take?
Sir, the length
Yes.
of the pipe. Sir, length of the pipe was given. Sir, उसको हमने कहाँ incorporate किए?
To compute the major loss of head, which
Okay,
is the FLV square over 2GD, and this D is small, ये वाला diameter, है ना?
Okay,
ये
sir.
capital D है. तो ये स्मॉल डी कर लें इसको।
ओके सर। और सर
हाँ जी।
साथ जो 0.5 v स्क्वायर ओवर 2g सर ये फ्लश लॉस है
नहीं, ये लॉस है ड्यू टू एंट्रेंस।
एंड
हमने पढ़े माइनर लॉसेस लाइक लॉस ऑफ हेड ड्यू टू एंट्रेंस, लॉस ऑफ हेड ड्यू टू एग्जिट। अच्छा, बाय द वे, व्हाई वी हैव नॉट टेकन लॉस ऑफ हेड ड्यू टू एग्जिट? माइनर लॉस होता है ना एग्जिट लॉस भी, वो क्यों नहीं लिया?
सर शार्प एज था कॉर्नर पे।
No, that was not the reason. If a pipe is discharging into water, then there would be exit loss. But as it is discharging into air, so there is no exit loss. And that's why we have not taken any exit loss. समझ आ गई?
यस सर।
ऐसे इधर है, दिस इज ए पाइपलाइन, दीज आर टू टैंक्स, एक ये टैंक है, एक ये टैंक है। तो यहाँ पे कौन सा लॉस होगा? एंट्रेंस लॉस। और इधर माइनर लॉस कौन सा होगा? एग्जिट लॉस। और इधर बीच में कौन सा होगा? लॉस ऑफ हेड ड्यू टू फ्रिक्शन। तो हियर द कंडीशन इज नॉट दैट वन, क्योंकि यहाँ ये फ्रीली एयर में डिस्चार्ज कर रहे हैं एट सेक्शन 2, सो देयर वोंट बी एनी minor loss of head at exit. So any other question? So shall we take break about 10 minutes?
Yes sir,
Okay.
नाश्ता करना।
अस्सलाम वालेकुम सर। डॉक्टर साहब अस्सलाम वालेकुम, मौजूद हैं आप?
जी जी,
अस्सलाम वालेकुम, कैसी तबीयत है?
अल्हम्दुलिल्लाह। आप कैसे हैं?
ठीक ठाक सर। मैंने कहा लगता ब्रेक है।
जी जी, ब्रेक है।
अच्छा अच्छा, गुड।
10 मिनट ब्रेक दी।
अच्छा अच्छा अच्छा, बहुत अच्छी बात है सर। आप ऑफिस से लेक्चर लेते हैं घर से भी?
नहीं नहीं, ऑफिस से जी, घर से नहीं।
नहीं, आप तो ऑफिस से ही होंगे सर, कुछ
हाँ, और बड़े काम होते हैं।
ठीक ठाक।
आप खैरियत से हैं?
जी जी सर, अल्लाह का शुक्र है।
अच्छा,
आज आप 12 बजे अवेलेबल होंगे? अगर हम एक थोड़ी सी स्टाफ की मीटिंग रख लें, आप भी आ सकेंगे?
इंशाल्लाह इंशाल्लाह।
अच्छा, ठीक है सर, थैंक यू।
ऑलराइट सर। क्यों भाई टाइम हो गया? Is break over? Excuse me.
जी सर।
भाई वापस आ गए?
Yes, sir.
Okay, shall
Yes,
we
sir.
continue?
Yes, sir.
Okay, now we also want to solve one more numerical for emptying time of the reservoirs. And now that is the problem number 3. A reservoir is circular in plan. If you see in plan, it is circular. It could be a square or rectangular, but this is circular. And when full, the dia of water surface is 60 meter. For example, if it is here, it is full, then the diameter is 60 meter. When water falls by 1.2 meter, the dia of the surface is 48 meter. So when this water level drops, so this distance, vertical distance is 1.2 meter, then the diameter of the surface, that becomes 48 meter. Discharge takes place through a 60 centimeter dia outlet. So there is an outlet or orifice, and its dia is 60 centimeter. Small d is 60 centimeter. 3 meter below the high water level, and this depth is 3 meter. So if this is 1.2 meter, then how much is this distance?
1.8, sir.
1.8 meter. So it means H2 is 3 meter and H1 is 1.8 meter. Which can be treated as orifice. So this can be treated as orifice with a CD value of 0.8. Now determine the time required to lower the water level by 1.2 meter. So how much the time would require when this level of water in the reservoir drops from this level to this level? Okay. It means when it drops by 1.2 meter, how much time it will take? When the reservoir is full at the start the reservoir is full. Suppose this is the maximum level of water which we can fill in the reservoir. Now this is a more complicated problem as compared to what we have previously solved. In this problem, it is not cylindrical shape overhead tank. Now what is the shape of the overhead tank? That is the frustum of cone. Frustum of cone. And this is the most useful form of the overhead tanks. Do you know what is the reason?
सर हाइड्रोलिक रेडियस ऐसे इसका मैक्सिमम एफिशिएंट इस वजह से
नहीं, कोई और बताए. Something else.
Sir, discharge constant rate. Discharge constant.
Sorry.
Constant discharge.
To improve the discharge like this.
सर जब इसका डायमीटर कम होगा तो डिस्चार्ज ऑलमोस्ट सेम ही रहेगा, मतलब सेम सप्लाई होगी वेलोसिटी.
No. Actually, the main reason to keep this conical shape is to easily flush the sediments which are deposited here in the reservoir. Could you follow why the shape is conical shape? Because when we fill water after long time, maybe after 1 year, तो इसमें थोड़े बहुत sediment तो होते हैं ना, they deposit here, and we need to clean them, and that is for easy flushing of the reservoir. Okay. Now here, do you think that what is the head? Small h. Small h is this value. So do you think the small h, this surface area is a function of h? क्या ख्याल है? Or it is independent of h? What is small h? That is head over the orifice. And you know, as the head increases, so this surface area also increases. It means वो जो हमारी equation है small t, that is integral area times dh divided by q1 minus q2. तो q2 तो function है ही है h का, but area is also now function of h. तो इसका मतलब है अब हमने दोनों चीजें as a function of h लिखनी है. And you know, first of all, we have to determine this diameter. Can we easily determine this diameter? कैसे मालूम करें? By considering the similar triangles, ये वाला और ये वाला. So this depth we know 1.2 meter और ये कितना होगा? 60 minus 48 divided by 2, 6 हो गया. So this 6 over 1.8 meter, this is 1.2. So the same as this depth, which is 3 meter over this x. तो ये x निकल आएगा. और जब ये x निकल आएगा, this distance. So how much is this? How we can compute this capital D? That is this 60 minus twice of this x, क्योंकि इधर भी है ना x. So this is how you can compute this diameter. So the solution is given here. So the same dimensions are mentioned: 1.2 meter, 1.8 meter, this is 60 meter, this you will get 30 meter, this you will compute basically, and this total depth is 3 meter. And now this is the main equation. First compute the area of the orifice, and that is 0.283 square meter. You will get the orifices here or here, doesn't matter. And then this is one way how to compute write the equation of diameter in terms of h, which is the head over the orifice. So simply we can make a graph. This is the one way in the diameter of the reservoir and the h. And let's say the graph is like that. So the slope of this line is 10, and you know, and this is the y-intercept is 30. You will get, so the diameter you can write this 30 plus 10 is the slope into h, and in this way you can write the expression for diameter in terms of h, which is the head. Now compute capital A. This is pi by 4 d square, means pi by 4, and d is 30 plus 10 h square. So this is a plus b square, and open it like that, 900 plus 608 plus 100 h square. And then the discharge would be equal to CD A to root of 2gh, and put values in terms of h. So you will get, this is the value of the Q2 or discharge, and then put values in over governing equation or the equation for emptying time. Small t is integral of minus a dh over q, and the put values here and here, and then simplify it, and finally you will get this equation. So now you have to do the integration of this, and it is very easy. h minus half की integration क्या होगी? h power half into 2, and so on. And then you will, if you will simplify it and apply limits, then the time to empty the reservoir from this level to this level would be 1,776 seconds. Any question? क्यों भाई? Are you sleeping or awakening? Are you awake?
Yes, sir. Yes.
Okay. So do you have any question?
यस सर, ये जो इक्वेशन बनाई है हमने स्लोप के लिए, ये कैसे बनाई है और 10 की वैल्यू कैसे है हमारे पास?
There are many ways to make this equation. The main idea is just to develop a relationship between diameter of the reservoir and the h, which is the head over the orifice. ठीक है ना? यहाँ पे orifice दे दिया है, doesn't matter. So this has been drawn because we know the value of the diameter at 2 value of h. 2h पे पता है ना? 48 or 60 meter. So 48 and 60 meter. What were the h values? We were not that. And then we can draw this line. And then from this slope of this line could be measured. And then we can also measure how much would be the y-intercept. So the equation of a straight line is y is equal to c plus mx. So d is the y and 30 plus 10 h, because 10 is the slope of this line. But anyway, you can also make by another way. There are many ways to derive this relationship. जी भाई.
सर अगर ये साइड लीनियर की बजाय अगर कर्व्ड हो,
No, then
केस में फिर इक्वेशन है.
No, then you need another equation. ये लीनियर, ये बिल्कुल स्ट्रेट है. अगर ये स्ट्रेट ना हो तो फिर वो हमें दोबारा इसका कर्व बनाएंगे और वहां से भी हम बना सकते हैं इक्वेशन, डजंट मैटर.
ओके,
ठीक हो गया?
यस
तो और अगर मैंने सारी खाली करनी हो तो फिर मैं क्या लूंगा? वैल्यू ऑफ h2 ये 0. वेरी गुड, 0 लूंगा, है ना? तो मुझे टाइम पता लग जाएगा कितनी देर में ये खाली होगी सारी. So these are the problem of unsteady flow. Shall we move forward? आगे चलें?
Yes, sir.
Okay. Now these all are practical problems, huh? Okay, now the discharge between two vessels or two tanks. Now if we have one tank here and another tank here, A1 is the surface area of the tank number 1, A2 is the surface area of tank number 2, and H1 is the initial difference of water level between these two tanks. This H1 is the head which causes the flow in this pipeline. And when this H1 will become 0, how much would be the velocity of flow in the pipeline? When the level of water here and here in both reservoirs would be same, how much would be the velocity of flow through the pipeline? कितनी होगी?
0.
0. There won't be any flow because there is no head which causes the flow. ठीक हो गया? So let in time dt the level of water goes down in the reservoir 1, and this drawdown in the reservoir 1 is dx, let's say. Then how much the water will rise when the same volume of water will flow from tank 1 to tank 2? तो उसमें rise कितना होगा? The rise would be A1 over A2 into dx. How we can prove it? This volume 1 is equal to volume 2. तो भाई यही करेंगे ना? Volume 1 is equal to volume 2. How you can compute volume 1? Area 1 into dx. यही होगा volume 1. That should be equal to area 2 into dx. sorry, area 2 into this value, let's say this y. So what is equal to then y? Area 1 over area 2 into dx. So this is the y. This is the respective change in the tank 2. Let's say after time dt, the difference of level between the two reservoirs is h2. ये h2 हो गया है ना after time dt. So now we want to derive the expression for it. And how many would be the losses? यहाँ पे होगा entrance loss, यहाँ friction loss, यहाँ exit loss. Okay, in the pipe. Let A1 and A2 are the surface areas of tank 1 and tank 2. And L is the length of the pipe, F is the friction factor of the pipe, small d is diameter of pipe, this diameter. Capital V is the velocity of water in the pipe. dx is the fall in water level in tank 1. And A1 over A2 into dx is the rise of water level in tank 2. Is it clear, Jay? All these symbols are understood by you?
Yes.
Sir, H1 and H2 को kindly explain कर दे. Sir, वो कैसे?
H1 जो है, that is the difference of water levels between reservoirs. Or H2, after some time, the difference of water levels after time dt वो H2 हो जाएगा, कम हो जाएगा ना भाई. जब फ्लो होता रहेगा तो क्या होगा, पानी इसका वाटर लेवल नीचे आएगा, इधर से ऊपर जाएगा, तो वो कम हो जाएगा. That is H2 after some time. And when the H2 will become 0, तो फिर फ्लो कितना होगा, फ्लो रुक जाएगा. So it means ये जो पाइप में फ्लो हो रहा है ये कौन सा है, स्टेडी है या अनस्टेडी?
स्टडी.
हाँ जी,
स्टडी.
वो स्टेडी कहाँ से हो गया?
Unsteady, sir.
Unsteady, because this H is keep on changing. Difference of heads between the two reservoirs is keep on changing. वो कम होता जा रहा है, इसलिए ये यहाँ पे वेलोसिटी भी कम होती जाएगी. और जब ये दोनों लेवल बराबर हो जाएंगे उस वक्त वेलोसिटी ऑफ फ्लो बिल्कुल 0 हो जाएगी. Okay, as velocity of flow and discharge is changing in the pipe, so the flow is कौन सा है, unsteady. H is difference of water level between two tanks. और वो किसके बराबर होता है हमें पता है ना, अगर हम एनर्जी इक्वेशन लगाएं, if this is section 1 and this is section 2, and if you apply energy equation, तो हमें क्या मिलता है कि जनाब ये H जो होता है वो समेशन ऑफ लॉसेस के बराबर होता है. और लॉसेस कौन से हैं, एंट्रेंस लॉस प्लस फ्रिक्शन लॉस प्लस एग्जिट लॉस. लेट्स से ये माइनर लॉसेस हम इग्नोर कर देते हैं, तो फिर हमारे पास सिर्फ मेजर लॉस रहता है, विच इज दिस डार्सी-वाइसबेक इक्वेशन से कंप्यूट करते हैं. एंड स्मॉल h इज FL(v²/2GT). तो यहाँ से वेलोसिटी की ये वैल्यू आ गई. लेट्स चेंज इन हेड इज dh. तो dh किसके बराबर हुआ, h1 माइनस h2. तो वो क्या इसके बराबर आता है, dx प्लस h1 area 1 over area 2 into dx. Is it clear this equation? Change in head h1 minus h2 किसके बराबर है, dx plus area 1 area 2 dx. Is it clear? भाई चेंज इन हेड क्या होगा, यहाँ इतना नीचे आया और इतना ऊपर चला गया है, यही चेंज इन हेड हुआ है ना. The water level in the tank 1 has gone down whereas it has gone up in the tank 2. तो ये dx है और ये area 1 over area 2 dx है, तो दोनों को जमा कर लें, which is we did here. Now is it clear? So from this expression dx क्या आ गया, area 2 over area 1 plus area 2 dh. And for time dt, volume out of tank 1 that is equal to velocity into area into dt. तो dt टाइम में टैंक 1 से कितना वॉल्यूम निकल रहा है पानी का, एरिया 1 इंटू dx, क्योंकि dx नीचे जा रहा है ना लेवल वाटर का, वो इस राइट हैंड साइड के बराबर है. सो dt वहां से क्या आ गया, वो ये आ गया 4 एरिया 1 dx पाई d स्क्वायर इंटू v. नाउ पुटिंग वैल्यू ऑफ v and dx from equation 1 and equation 3 in equation 5. इस equation 5 में ये दो वैल्यूज v और dx की डालें तो equation 6 आ गई dt is equal to that. अब dt डेरिवेटिव है, उससे जान छुड़ाने के लिए we have to do the integration. So जब हमने इंटीग्रेशन की तो ये टाइम आ गया, एम्प्टिंग टाइम, that is equal to integral with limits h1 to h2 and this whole into dh. And when you will integrate it, तो इसमें सिर्फ ये रूट ऑफ h है जिसकी इंटीग्रेशन होनी है ना, तो that is the time is equal to 8 a1 a2 pi d square a1 plus a2 root of fl 2gt under root h1 minus h2. So this is the equation number 7, and this is to compute the emptying time from for a reservoir when the water level reduces from the H1 head to H2 head. Is it clear, जी? समझ आ गई?
Yes, sir.
Very good. Now we have to apply this equation. Problem number 1. Okay, क्योंकि अब केस चेंज हो गया ना. Two water tanks A and B whose cross-sectional areas at 8 and 4 square meter respectively are connected by a 5 centimeter dia pipe 120 meter long having friction factor this much 0.04. If the initial difference of level is 1.5 meter, so H1 is 1.5 meter, find the time taken for 2 cubic meter of water to pass from tank A to tank B. Now they have not given us the value of H2. So H2 we have to determine by ourselves, okay? But they have mentioned that from tank 1, 2 cubic meter of water has gone into tank 2. So this is the solution. So this is the tank A, this is the tank B, and this is a pipe of length whatever is given 120 meter and so on. So it is given that the volume in the tank 1 V1 is equal to area 1 into dx. So this 2 cubic meter is going from this tank to, so 2 into dx, it means dx is 0.25 meter. So this drawdown in the tank 1 would be 0.25 meter. Now we have to compute H1. And from the equation of H1, basically we will compute H2. And H1 क्या है? The level of water from here to here जो original है. So that is 1.5 meter as it is given, and dx is 0.25 plus H2 which we want to determine plus area 1 over area 2 into dx. We know that it is given that the area, the surface area of tank 1 is double of surface area of tank 2. So this is ratio is 2 into dx is 0.25, and from this equation H2 you can easily determine it is 0.75 meter. Now we know the H1, we know the H2, and we know these all FL and small d, and this is the equation to compute the emptying time to drop the change in head from H1 to H2. So just put values, and we have substituted the values, and the time we finally got 2155 seconds. So any question you have? कोई मुश्किल तो नहीं है? Excuse me, do you have any questions?
No, sir.
Okay, shall we move next? Okay, now we want to
Yes, sir.
solve one more numerical. It is not numerical, it's a derivation. Instead of pipeline between two tanks, if the both tanks are connected with an orifice, I mean, this is just a vertical wall having an opening here. Then water go from the higher water level tank to the lower water level tank. And this flow through the orifice would be steady or unsteady?
Unsteady.
Unsteady.
Unsteady. Now what is our problem 2? Show that when flow is taken place between two vessels means tank, this and that, through a sharp-edged orifice. So this is a sharp-edged orifice of area A, small a is the area, ye wala A, and CD, coefficient of discharge, इसका coefficient of discharge CD है, time required for the change of difference of level from H1 to H2. Okay, and we know what is H1 and what is H2. H1 and H2 are the difference of levels. So R unsteady flow through orifice between two vessels. So that is this case, and the final equation, what he's asking, that prove this equation, that this time taken is 2 area 1 area 2 over area 1 plus area 2 under root H1 minus H2 over CD a root of 2G. Now we have to derive. So this is the same diagram, and let's say this drawdown is dx. तो यहाँ से rise कितना होगा? Area 1 over area 2 into dx. So this is the H2. Then the H2 is the new difference of levels between reservoirs after time dt. Now let H is the difference of level at any time. Then what would be the velocity of flow through the orifice? That is root of 2gh. Then what would be the discharge? CDA root of 2gh. This is equation number 1. And we know that dh, which is the change in head, would be dx plus area 1 over area 2 into dx. ये नीचे आएगा, ये ऊपर जाएगा, दोनों को जमा कर लें, that is the change in head. Therefore, dx from this equation would be area 2 over area 1 plus area 2 dh. And for time dt, volume out of reservoir would be CDA root of 2gh into dx. And from here, if you will, how much is volume for time dt? Volume of water which will lose the reservoir 1 would be area 1 into dx. From this equation, you will get the equation of dt, area 1 dx, CDA root of 2gh, substituting value of dx and which is from equation 2. So the dt will become like this, and so instead of dt, if you want to compute t, then you have to integrate this equation, and integrating it h power minus half dh को अगर आप integrate करेंगे, the final equation you will get this. So small t is 2 area 1 area 2 area 1 plus area 2 1 over CDA root of 2g under root h1 minus h2, and this is proved. So please do practice of proving this by hand. Then you will understand these concepts. Shall we move ahead? आगे चलें? I think all are sleeping.
No, sir. No, sir.
सर आज के लिए काफी नहीं हो गया?
नहीं, बस एक और सवाल कर लेते हैं. We will do one more numerical problem, and then we will stop today this chapter. Challenge next.
Okay,
we
sir.
want to solve a numerical problem number 3. A rectangular tank 4 meter long and 2 meter wide. 4 meter लंबा है, 2 meter wide है. Is divided into 2 parts. अब 2 parts में divide कर दिया ये tank. by a vertical dividing plate। वर्टिकल प्लेट बीच में लगा दी, तो ये था 4 मीटर बाय 2 मीटर था, तो कहीं हमने ना वर्टिकल प्लेट लगा दी। कैसे लगाई? so that the capacity of one portion is twice of the other। अब एक पोर्शन जो है कैपेसिटी उसकी डबल है, its capacity is double as compared to second tank। The dividing plate has a square sharp edged orifice। अब ये जो orifice है बीच में, ये सर्कुलर नहीं है, its shape is square and its one side is 2.5 centimeter through which the flow takes place। Okay, at first the level of water in the longer portion is 2 meter above that in the smaller। So difference of water levels is how much in the beginning? 2 meter। So it means H1 is 2 meter। Determine the time taken for this difference of level to be reduced to 1 meter। So H2 is 1 meter। Also calculate the time for the levels to be equal। दोनों के equal हो जाएंगे तो what would be the value of H2?
0।
When the water level in both the tanks would be same, then H2 will become 0। तो वो कह रहा है वो जब H2 0 हो जाएगा वो टाइम भी निकालो। For orifice take CD is equal to 0.6। all right, that is the problem। So it means what we have to do, we have to simply apply this equation, है ना? ये equation लगानी है और कुछ भी नहीं करना। और but in this equation we need the value of H1 and H2 and area 1 and area 2। So do we have area 1 and area 2? Do we have? We do not have। सिर्फ यही बताया है कि एक बड़ा टैंक था, its length was 4 meter, its width was 2 meter in plan, and then a vertical wall was inserted, vertical plate was inserted inside, जैसे 2 टैंक बन गए। और लेकिन ये बताया कि इस तरह बनाए हैं कि एक टैंक का एरिया डबल है as compared to second tank। But we do not have values of A1 and A2, तो इसमें हमने पहले वो values of A1 और A2 निकालनी है। The value of H1 and H2 are given, so means we can easily solve the problem। So the solution is given here। So this is the section of the tank। तो ये section है, इसकी लंबाई 4 मीटर है, and this is the plan of the tank। So width is 2 meter, length is 4 meter, and here this is the water level and this is the water level। So initial जो difference H1 है, it is the 2 meter, and here there is an orifice। The shape of this orifice is a square। Now so what is the total area? Total area would be this into that, 8 square meter। Okay, now this is given that volume 1 is twice of volume 2, so it means area 1 is twice of area 2। okay, means the total जो capacity है of this tank is equal to the total capacity double of this tank 2। दूसरी जो इक्वेशन है वो हमारी क्या बनेगी कि जो इसका सरफेस एरिया है और इसका सरफेस एरिया है, दोनों को अगर जमा करेंगे तो कितना होना चाहिए? 8 स्क्वायर मीटर। ऑलराइट, सो वी हैव दीज टू equations with how many unknowns? With 2 unknowns, so we can determine A1 and A2 both, and then A2 comes 2.67 square meter and A2 will be total 8 है minus area 1, then this is the area 2 5.33 square meter। So the surface area of tank 1 is 5.33 square meter, surface area of tank 2 is 2.67 square meter। So area 1 and area 2 we have determined। Now we need to compute this area of the orifice, small a, which is 2.5 centimeter divided by 100. Take its square because it is square in shape. So 0.000625 square meter is the area of that orifice. And now we know the area 1 and area 2 and small a and h1 and h2. So we can easily use this equation for orifice. The flow of water between two tanks through an orifice, and once you will substitute these values, then you will get time 887.2 seconds to fall the when the this difference of water levels changes from 2 meter to 1 meter. And this is the answer when the difference of water levels changes from 2 meter to how much? H2 becomes to 0 meter. So that time is 3029 seconds. Is it okay?
Yes, sir.
Yes, sir.
All right. So do you have any questions till now? Now you can feel that how important is unsteady flow problems. How important are unsteady flow problems? So real problem जो हैं, many real problems of the open channel flow and pipe flow, they are unsteady.
सर जिस टाइम H2 0 होना है तो उस टाइम जो H1 होना है वो हम 1 मीटर कंसीडर करेंगे.
No, H1 is 2. Actually, what is being asked, ke H1, if it is 2 meter, then how much time would be required to become H2 0 meter? तो आप H1 को 2 मीटर ही लेंगे, ठीक है, और H2 को 0 डालेंगे. Any other question? Okay, what is then the general equation we have derived for emptying time for a reservoir? वो क्या थी? Can anybody repeat? Wait. Small t, that is equal to integral h1 h2 area times dh divided by q1 minus q2. यही है?
Yes.
Yes, sir.
Actually, this is the basic equation to compute emptying time for a reservoir. और अभी तक हमने जो डिस्कस किया है उसमें what is the governing equation? That is this equation. यही है ना emptying time निकालने के लिए. And you know it is very important to compute the emptying time for a reservoir. So mainly till today what we have discussed, we have derived I think 3 equations. One is the this equation small t, that is integral h1 to h2 area times dh divided by q1 minus q2. This is the general equation. दूसरी कौन सी हमने इक्वेशन डिराइव की है? That is the case number. That is this one. If we have the same reservoir को बगैर इंटीग्रेशन के अगर हमने करना हो तो emptying time is 2a CDA root of 2g h1 minus h2 है, ठीक है. And here h1 and h2 are the head over orifices. Then we have derived this equation when there is a pipe, when two reservoirs are connected with a pipeline, तो फिर हमारा एम्प्टिंग टाइम किसके बराबर है 8a1 a2 पाई d स्क्वायर a1 प्लस a2 fl ओवर 2gd a under root h1 minus under root h2. The next equation which we have derived is when the two tanks are connected with an orifice, then the emptying time is this one 2a1 a2 over a1 plus a2 and into h under root h1 minus root of h2 over cdA root of 2g. So these equations today we have derived, and we also have solved numericals to understand these equations. So with that, shall we stop? क्यों जी ठीक है?
यस सर।
Yes, sir. काफी बेहतरीन।
कोई क्वेश्चन है तो पूछ लें। If you do not have any question, हाँ अटेंडेंस ले लेते हैं। बहुत शुक्रिया अटेंडेंस की याद दिलाने का। ये लें जी, ये अटेंडेंस डाउनलोड अटेंडेंस लिस्ट हो गई जी अटेंडेंस। So now I would like to stop the recording.